Imagine a game of cosmic dice where the outcome is not a fixed number, but a blur of possibilities. Each roll of the dice opens up a myriad of potential outcomes, each as likely as the next. This is the strange and wonderful world of quantum mechanics, the theory that governs the behavior of matter at its smallest scales. Here, the rules of classical physics no longer apply. In this realm, particles like electrons don't behave like tiny billiard balls, but rather like ripples on a pond spreading out and interacting in ways that defy our everyday experiences. Their properties are smeared out in a haze of probability, making it impossible to pinpoint their exact location or momentum. At the heart of this quantum weirdness lies the wave function, a mathematical tool that describes the state of a quantum system. It encapsulates all the possible states a particle can be in. Unlike classical physics, where we can precisely determine the position and momentum of an object, the wave function only gives us probabilities. It tells us where a particle is likely to be found, but not with certainty. Imagine trying to pinpoint the location of a raindrop in a downpour. You know it's somewhere in the storm cloud, but you can't say exactly where until it falls. This is akin to the uncertainty we face in the quantum world. Similarly, the wave function tells us the likelihood of finding a particle at a particular point in space and time. It's like a map of possibilities, a guide to where a particle might be, with peaks representing areas of high probability and troughs indicating regions where the particle is less likely to be found. This map is constantly changing, influenced by interactions and measurements. But until we make a measurement, the particle exists in a superposition of states, a blend of all possible outcomes, a kind of quantum limbo where it's potentially everywhere and nowhere at the same time. This superposition is a fundamental aspect of quantum mechanics. This inherent uncertainty is not due to a lack of knowledge or experimental limitations, but a fundamental property of the quantum world. It challenges our classical intuitions and forces us to rethink the nature of reality. The act of measurement itself forces the particle to choose a specific state, collapsing the wave function from a wave of possibilities into a single, definite outcome. This collapse is instantaneous, a sudden transition from uncertainty to certainty. Quantum mechanics also introduces the concept of entanglement, where particles become linked and instantaneously affect each other, no matter the distance. This phenomenon defies classical explanations and suggests a deeper, interconnected reality. Understanding and harnessing these quantum principles is leading to groundbreaking technologies such as quantum computing, which promises to revolutionize our world. As we continue to explore this uncertain world, we uncover new layers of complexity and potential, pushing the boundaries of what we know and what we can achieve. The journey into the quantum realm is just beginning, and it holds the promise of unlocking the deepest mysteries of the universe. In this uncertain world, every discovery is a step closer to understanding the true nature of reality. Think of the wave function as a surfer riding a wave. Imagine the thrill and the challenge of balancing on the crest, feeling the power of the ocean beneath you. The surfer represents a particle, and the wave itself is the mathematical description of the particle's state. This wave is not just a simple sine curve, but a complex, multidimensional entity that encapsulates all possible states of the particle. Just as the wave guides the surfer's motion, the wave function dictates the behavior of the particle, determining the probability of finding it at different points in space and time. The surfer's path is influenced by the wave's shape, speed, and direction, much like how a particle's position and momentum are influenced by its wave function. The height of the wave at a particular point corresponds to the probability of finding the particle there. A towering wave crest signifies a high probability, a place where the particle is most likely to be found. A tall, cresting wave indicates a high probability, while a low trough suggests a lower likelihood. The undulating nature of the wave mirrors the fluctuating probabilities of the particle's presence. As the wave propagates, so too does the particle, its position constantly evolving according to the dictates of the wave function. The surfer must continuously adjust to the changing wave, just as the particle's state is in perpetual flux. Just as a surfer can ride different types of waves, gentle rollers or towering breakers, particles can exhibit different wave functions depending on their energy and environment. Each wave function is unique, shaped by the particle's interactions and the forces acting upon it. The wave function is not a static entity, but a dynamic, ever-changing description of the particle's quantum state. It evolves over time, influenced by external factors and internal properties, much like how ocean waves are shaped by wind, tides, and underwater currents. However, there's a crucial difference between our surfer analogy and the reality of the wave function. While a surfer can pause, reflect, and choose their next wave, a particle is bound to its wave function without such freedom. Unlike a surfer who can choose to jump off the wave, a particle is inextricably bound to its wave function. It cannot escape or separate from this mathematical description. It is an inherent part of its existence. It's not simply riding the wave, it is the wave. Its very existence spread out across space and time according to the probabilistic dictates of this mathematical entity. The particle and its wave function are one and the same, an inseparable unity that defines its behavior and properties in the quantum realm. Let's imagine an electron orbiting an atom's nucleus. In classical physics, we might picture this electron as a tiny planet circling a sun, following a predictable path. However, in the quantum world, things are far less certain. We can't pinpoint the electron's exact location at any given moment. Unlike the neat little orbits we draw in textbook diagrams, the reality is much more complex and intriguing. Instead of a fixed path, we have the electron's wave function, which manifests as a blurry cloud surrounding the nucleus. This cloud isn't just a random blur. It represents the probability of finding the electron at different points around the nucleus. The denser the cloud in a particular region, the higher the probability of finding the electron there at any given time. Conversely, sparser regions indicate a lower probability of the electron being found in those areas. It's akin to trying to pin down a cloud of smoke. The smoke has a presence, but its shape is constantly shifting, making it impossible to define its boundaries precisely. Now, let's say we attempt to measure the electron's position. This act of measurement is crucial in the quantum realm. Measuring the electron's position is like shining a bright light on our smoke cloud. The light interacts with the smoke, altering its state. The moment the light hits, the smoke particles scatter and the once amorphous cloud collapses into a more defined shape, albeit temporarily. Similarly, when we measure the electron's position, its wave function collapses and the particle chooses a definite location. Before the measurement, the electron existed in a superposition of states, potentially occupying all points within the cloud simultaneously. The act of observation forces the electron to snap out of this limbo and assume a specific position, a phenomenon that defies our classical understanding of reality. This doesn't mean the electron was hiding at that location all along, waiting to be discovered. Instead, it means the act of measurement itself influenced the outcome, collapsing the wave function and forcing the electron to materialize at a particular point. This inherent randomness is a fundamental aspect of quantum mechanics, making the world a much stranger and more uncertain place than classical physics ever imagined. This concept is closely tied to Heisenberg's uncertainty principle, which states that we cannot simultaneously know the exact position and momentum of a particle. Another famous illustration of quantum uncertainty is Schrodinger's cat, a thought experiment that shows how particles can exist in multiple states until observed. Quantum mechanics also introduces the idea of entanglement, where particles become interconnected, and their cat and the mass and the state of one instantly influences the state of another, no matter the distance. These strange and fascinating principles are not just theoretical. They have practical applications in emerging technologies like quantum computing, which promises to revolutionize how we process information. The quantum world challenges our perceptions and invites us to explore a reality that is far more complex and mysterious than we ever imagined. As scientists continue to delve into the quantum realm, we can expect to uncover even more astonishing truths about the nature of our universe. From the tiniest particles to the vastness of the cosmos, the principles of quantum mechanics remind us that the universe is full of wonder and surprises waiting to be discovered.